This is video number 2 for Mr. Sweeney's AP Physics C class. Today we're going to be talking about vectors and projectile motion. And we'll start by talking about what a scalar is. A scalar is any value that does not have a direction associated with it. Oftentimes a scalar is represented as a magnitude. A vector, on the other hand, is any quantity that has both a magnitude and a direction. And examples of vectors versus scalars would be a speed as a scalar value, so you might say 20 meters per second. But for a vector value, that would be velocity, it would be 20 meters per second north. And the difference between the two is the direction. When we talk about vectors, one of the most useful things about vectors is that they can be represented graphically by an arrow. When you look at an arrow, the length of the arrow itself represents its magnitude, and there must be some sort of scale that identifies what length the arrow is drawn to, what physical quantity it represents, and the scale might be, say, 1 centimeter equals 1 meter per second. So that way you can determine, based on the length of the arrow, exactly what magnitude of the value it has. The arrow direction on any graphical vector, of course, shows the direction in which the vector would be pointing in. Speaking of vector directions, when we look at vectors, the direction of a vector can only be given with some sort of reference to a coordinate system. Typical coordinate systems you'll see in this class include XY Cartesian coordinate systems, as well as cardinal coordinate systems that would be north, south, east, and west. When trying to decide what coordinate system you're going to use, you should take whatever lead has been given by your problem. So if the problem is using north, south, east, and west, you'd use that. If it's using right and left, you'd use that. If it's using x direction and y direction, you'd use that. If no coordinate system is given and no one is implied, feel free to choose any particular coordinate system that fits your example. Another thing that is often done with vectors is vector addition. Vectors can be added graphically or mathematically. When you add vectors graphically, you use the head to tail method, meaning that you start each vector at the head of the preceding vector so that the tail of the second vector comes in contact with the head of the preceding vector, hence the head to tail method. To find the resultant or the ultimate or the overall result of the vector addition, you would produce a third vector that goes from the tail of the first vector to the head of the last vector, and that's referred to as the resultant. If you start with a vector that's already in 2 dimensions and instead want to go and figure out how that vector is represented in dimensions or directions that are significant, you can go into vector components. Typically, when you calculate the vector components of any particular vector, it's going to be some trig function, and you see that in the diagram below, where you have vector A that has been split into x and y components. In that vector information, which should primarily be review. If anyone has any questions about vectors, they can see me in one of my free periods. We're going to move on to another review topic, that is of projectile motion. A projectile is referred to as any object that is acted upon only by gravity. This can include projectiles that are moving in 2 directions or projectiles that are moving up and down vertically just under the effect of gravity. In projectile motion, acceleration due to gravity is negative 9.8 meters per second squared. The negative is referring to the downward direction. As a convention in this class, which I would like to adopt for the class as a whole, I will use the downward direction as negative so we can stay consistent. Finally, when you talk about projectiles that are moving in 2 dimensions, those will always produce parabolic arcs. That path of a projectile, the parabolic arc that it takes, is referred to as trajectory. Now on the diagram below, you can see that we have an object that has been projected with an initial velocity v sub 0, which is shown by the black vector arrow. The blue line the blue dotted line is level ground, and the red dotted line is the trajectory of the projectile. Please note that the trajectory of the projectile does not start at the tip of the arrow. Instead, it starts to deviate from the vector that the initial velocity was initially on immediately. When we look at factors that are affecting trajectory, there are two primary ones that we're going to look outside of friction, which we will talk about later, and those two are angle and initial velocity. So whatever initial velocity and angle a projectile starts with, those are going to be the two factors that affect its trajectory when we disregard any frictional forces. At the heart of our analysis of projectile motion is this idea of independence of motion. When we look at the motion of any projectile, however it's moving vertically and horizontally can be analyzed independently of each other. The vertical motion is a motion that has acceleration that's acting only under gravity, that's 9.8 meters per second squared, while horizontally there is no acceleration, so there will always be a constant velocity in that direction. Now the time at which the two motions are happening can be related to each other through time. So typically we look at vertical motion, we look at horizontal motion, and we bring them together based on how long it takes them to get to their respective positions. If we isolate and just look at the vertical motion, here we have a negative 9.8 meters per second squared as the acceleration due to gravity. The initial velocity, if it's an angled projectile, meaning one that is launched that is not purely vertical, is a component of whatever the initial vector velocity is. So you'd have to do some trig to find what the initial velocity is. And then all motion in the vertical direction should have the y subscript of y, just to let everyone know that this value is in the vertical direction. We'll have different sets for horizontal and vertical motion. In that vertical motion, it is identical actually to how a freely falling object is looked at. So we've already looked at free fall, which is one-dimensional projectiles, either objects thrown up in the air or dropped from a height. Once you get an initial velocity vertical for any projectile, you could treat the remainder of the analysis in the vertical direction as a free fall problem. Time is always determined, and by time I mean the time that an object is in the air is always determined vertically. That'll never be something that is determined horizontally. And when we look at our kinematic equations, these are the ones that we use with the free fall because they have acceleration due to gravity. The three kinematic equations listed below are the ones we use to solve for the motion vertically. Horizontally, because there's no acceleration, gravity only acts vertically, the velocity that is there horizontally will always remain there horizontally. The initial velocity can either be found as a component or it may be given to you in the problem. In the horizontal direction, because there's no acceleration, we use just the velocity equals displacement divided by time. So we can figure out range, how far down some projectile has traveled, time, velocity, all using v equals displacement divided by time. So looking at this, really we're going to see two sorts of projectile questions or problems in our studies. The first one is going to deal with a horizontal projectile, a very common type of projectile. In this scenario, again, no horizontal acceleration, but because it's horizontally projected, it also begins with zero initial velocity. So any horizontal projectile, we always start with certain amounts of things that we already know. First, in the vertical direction, acceleration is always going to be negative 9.8 meters per second squared. And then initially in the vertical direction, it will have a velocity of 0 meters per second, but that will change with time every second, increasing by 9.8 meters per second squared vertically. Of course, in the horizontal direction, as in all projectile problems, the velocity is going to be constant. So let's take a look at an example of a horizontal projectile. In this example, Boba Fett rids himself of two rival bounty hunters by dropping them off a 15-meter high cliff. He drops one directly off the edge, but the other one has upset him, so he decides to fire the second unfortunate bounty hunter out of cannon instead. The two bounty hunters hit the ground 42 meters apart, and what the question wants to know is what did the bounty hunter was fired from the cannon, what velocity did that bounty hunter leave with? In this question, we have a couple things that we're looking at. First, they give us a range in there, that 42 meters. Second, they give us a height that the cliff is off. And both of these are important in trying to figure out what this is. In order to find what velocity the horizontal bounty hunter left the cannon with, we need to figure out how long he was in the air for, because velocity equals displacement divided by time. We already have our displacement. If we had our time, we'd be able to find this velocity. Now, the two bounty hunters, because of independence of motion, will still hit the ground in the same amount of time period when fired. So if we could figure out how long it took the first bounty hunter to hit the ground when dropped off a 15-meter high cliff, we could figure out how long the second one was in the air, thereby determining what the velocity is. So our first step is finding the time, and our second step will be finding the velocity. So to find the time, we use this equation. Y, or displacement vertical, equals the initial vertical displacement plus velocity initial vertical times time plus 1/2 at squared. Now we know we end when he hits the ground. That would give a y value of 0 meters. We know that it's dropped from 15 meters high, so that would be initial position would be 15 meters. And we know because it's a horizontal projectile, there's no vertical velocity, or there's no vertical velocity to begin with. So that second term really goes to 0, and we're simply left with 0 meters equals 15 meters plus 1/2 9.8 meters per second squared time squared. And solving this equation for time gives us 1.75 seconds. Note that because you're subtracting 15 from 0, you get negative 15 on the left-hand side of your equation, which with the negative 9.8 meters per second squared allows us not to have to try to take the square root of a negative number. Once we have that 1.75 seconds, we can find the velocity. Velocity is going to be equal to the displacement divided by the time. We know our displacement is 42 meters. We also know that the time frame that it occurred over was 1.75 seconds. So 42 divided by 1.75 lets us figure out the velocity the bounty hunter was launched with, and that is 24 meters per second. And this type of problem is a common one. The other common type of problem we see with projectiles is angled projectiles. Now for angled projectiles, this is any projectile that is launched with an angle that is not in the horizontal or the vertical direction, but somewhere in between. That means it has an initial velocity in both the x and y directions. Whenever you start an angled projectile problem, our first step is always to split this initial velocity into vertical and horizontal directions. That way we can analyze both directions independently. There are a couple things that we go into these angled projectile problems with. The first being acceleration due to gravity, being negative 9.8 meters per second squared. We know that when the projectile hits its peak, if it's launched at an angle, that means it's going to rise for some period before it gets to the top. When it hits its peak, it's going to have a velocity of 0 meters per second. And finally, we know that in the horizontal direction, whatever velocity we begin with will be constant. Now there is an example in your notes of a projectile launched from level ground with initial speed of VO and an angle of theta. Neglecting air resistance, which is friction, they want to know how long the projectile remained in the air in terms of initial velocity, gravity, acceleration due to gravity, and theta. So for this problem, I'd like you to try this problem on your own, and then we will take a look at that when you next return to class. And that will wrap up the notes for this section. We'll do the rest of this note packet in class.